Okay, so thanks a lot. Thanks for the invitation. Thanks for the introduction. And I have to apologize. I woke up with kind of a bad voice, so I'm not sure how it will go during this talk, but I will try. So it's a joint project with Justus Bruckamp, who is a PhD student in Osnabrück, Lina Goltermann, who is in Bochum now as a master student, Erik Landin, who was a master student at KTH, Liam Solus, who is at KTH, and Lorenzo Venturello, who is in Siena. And there will appear more people, but these are the people, I think most of the results are with these people. And before we start, let me just tell you briefly, okay, this worked before. Let me just tell you briefly what's the plan. So I want to start by telling you what are cosmological polytopes, why are they interested, not besides just being nice lattice polytopes, also why do physicists actually care for these polytopes. And the second part, I want to provide you a Gröbner basis, and from this we will go to a regular unimodular triangulation for these polytopes. In the third part, we will apply what we've seen here to compute H-star polynomials in certain cases. And the last part is kind of to motivate you and to convince you that these polytopes carry a lot of nice combinatorics and geometry which we just don't understand. And it's really worth to look at these polytopes, and there's a lot of things one can still do. So in the last part, I will just throw a lot of things at you without, let's say many proofs at all. So what is the cosmological polytope? So you start with a graph G with on vertex Z V and edge Z E. And this graph just should not have isolated vertices. However, it's allowed that you have multiple edges. So this is fine. It does not have to be a simple graph. And then you define a polytope, which is a lattice polytope, which lives in R to the V union E. So you have a coordinate for each vertex of your graph and for each edge of your graph. And so what are you going to do? You take an edge of your graph, let's say F from I to J, and then you associate 3 lattice points to this edge. And the way you are going to do this is as follows. So we have one coordinate for F, which is given by this, which corresponds to this unit vector corresponding to F. We have one coordinate for the vertex I, and we have one coordinate for the vertex J. And then somehow you take these 3 unit vectors and you place exactly 1 minus 1 in front. And you take a plus for the other ones. So let's look at an examples to see what's happening.
Why did you choose those 3 sign patterns out of the possible 8?
Because I will tell you that the polytope is motivated from physics, and there it comes with a canonical definition. So it comes from there. It was not my idea to define it. Also the name.
I wasn't criticizing it.
Also the name comes from cosmology. But anyhow, let's talk about this later a little bit. So let's start with this edge. So I have a vertex 1, I have the vertex 2, I have the edge from 1 to 2, which I call F. So now I have 3 coordinates. Let's say the first coordinate corresponds to vertex 1, the second to vertex 2, the third to the edge F. And then I have these 3 vectors, which is 1, 1, minus 1. So here I take a minus 1 for the edge. Here I take a minus 1 for vertex 2. Here I take a minus 1 for vertex 1. So if I do this, I just get this triangle. And what you can notice is, so first of all, this polytope is not full dimensional, just because the sum of the entries is always 1. So this lives on the hyperplane that the sum of the coordinate equals 1. Second thing is that whenever you have let's say if we take this vertex here and take this vertex here, then the midpoint is a unit vector corresponding to vertex 1. Same here, the midpoint is a unit vector corresponding to vertex 2. Same here, midpoint is a unit vector corresponding to the edge. So you will have all unit vectors inside, which already tells you that this has codimension 1. And the other observation, which I already just said, is we will always have the unit vectors occurring as lattice points. But beside the vertices, these are all lattice points inside this polytope. And I already, in order to make it easier, so there is a picture of this specific example, and you don't have to look at everything which is written there. It will become clear. but I wanted to have it on the board for you to make it easier to follow. Okay, so why do physicists care for these polytopes, and why do we care? So it's motivated by physics. So in cosmology, there's something which is called the wave function of the universe, or flat space wave function, however you prefer. And I won't tell you what it is, and I think I don't really know. What I know is, so don't ask too many physics questions, but what I know is that there is something which is called the canonical form of a polytope. And in this case, it's canonical form of the cosmological polytope. So very roughly, what is it? So it's a differential form, so omega is a regular differential form on this polytopes, and in the denominator, you have a product of linear forms, and these linear forms just define the facets of the polytope. So if you know the polytope, if you have a facet description, you can write down the denominator. The enumerator is more difficult, so it's a polynomial which vanishes on intersection of facets of the polytope, but only those which do not lie inside the polytope. So basically, you take two facets which don't share another face, and you intersect them. And in particular, if you just have a simplex, then this polynomial g will just be 1. So it's extremely simple in this case. And then there is a certain sign. So you have to orient stuff, but roughly that's it. So one way to compute these canonical forms is to take a subdivision of the polytope into smaller polytopes, and then this canonical form is additive. So instead of computing the canonical form of the cosmological polytope, you can just sum up the canonical forms of these smaller things. In particular, if you have triangulation, then as I just said, you have a 1 in the numerator. So you only have simplices, so this is kind of an easy case. Okay, so questions so far? Okay. So what do physicists want to know? Okay, so one question we got from them when we started speaking to physicists is, what nice subdivision do these polytopes have? And I have a quote here from Paulo Benincasa, who is in Munich. So he said, certain subdivisions of CG have been shown to correspond to classical theories for computing wave functions. Pretty much anything you can say about this polytope is interesting because it probably has some physical interpretation. So tell this a mathematician, and then he's happy. And just to add a question, so what other nice properties do these polytopes have? And so let me say what was known, or what is known. So there's a paper where these polytopes were introduced in 2017 by Arkani-Hamed, Benincasa and Postnikov, where they provide a facet description. And don't expect this facet description to appear in the theorem. There's not a single theorem in this whole paper. It's just like somewhere written, and the proof is beautiful, but you wouldn't call it a proof. I mean, it's not written as a mathematician would write it. But nevertheless, it's a great paper. And then later on, there was the face description provided by Benincasa and Gröbner in 2 different papers. And in the same paper, they could also compute the normalized volume in the case that the underlying graph is a tree. Okay, so this was somehow the state of the art. So let me directly go to triangulations, or let's say Gröbner bases. Let me start by setting up some notation. And so let me start by defining the toric ideal, but I don't want to do it in general. I just want to do it for this very specific case of like cosmological polytopes. So we are taking our graph on vertex ZV, edge ZE, and then we define a polynomial ring where the variables correspond to the lattice points of the polytope. So we have a variable which I call CK, which corresponds to the unit vector for this vertex. We have seen this is a lattice point. We have a similar variable CE, which corresponds to the unit vector corresponding to an edge. Then there are 2 variables, yij and yji, also corresponding to the edge E, where yij corresponds to the lattice point where I have a 1 for vertex I have a -1 for vertex j, and I have a 1 for the corresponding edge, and similar for yji. And then finally, this TE is a variable which corresponds to the vertex where I have a -1 for the edge variable. And I've drawn this here so that it's easier to remember. So you have the graph, you have the vertices, you have the corresponding variables also. And there will come some graphic representation of these things which will make our life easier. So now what are we going to do? So now we take this polynomial ring and we map the variables to the corresponding lattice points somehow. So here I have a monoid algebra where the generators correspond to the lattice point in the polytope. And then what I'm doing is just to say, okay, this vertex ck, I map it to it's the unit vector. So here I take x to the corresponding exponent, which just gives me the variable xk, similar for xe. Ce maps to xe, and then yij is just saying, okay, I have this vector where I have a 1 for I have a -1 for j, and I have a 1 for e, which gives me this xi, xj minus 1, xe. Same thing here, and finally for this te, this is a vertex where I have 1 for I, 1 for j, -1 for e, so I map it to xi, xj, xe to the -1.
So are those last three exponent vectors the same as the three vectors you showed us on the first slide?
Sorry?
What?
Sorry, I didn't understand it, sorry.
In exponential form, are those the same three vectors I asked for about before?
Yeah. And now I take the kernel of this ideal, of this map, and that's the toric ideal. So let's look at an example. And then let's look at the easiest example, namely an edge. And okay, what you see here, you already have 6 generators in this case, and we just have 1 edge. So it's like, it's not that like, but the thing is that you will always, these generators will always appear for every edge in your graph. This is also clear. So for every edge, I will have these generators, no matter how my graph looks like. And so let's go on, let's see what we do. So what we do here now is we order our variables, and I take Lex order with respect to this ordering of the variables. So I first take, so the biggest variables are the ones where I have like the -1 in one of the vertex positions, then I have the last vertex, and then I just have the unit vectors. And if I do this, so yeah, I've spelled out what is the Lex order, which is not that important, but if I do this right now, what we see is the leading terms. So the ones which are bigger in this order are the underlying terms. So these are in particular square-free. And now you could ask, okay, is this all? So if I pass to a general graph, are there more generators? And yeah, the answer is no, it's not all. Even if you pass to like this easy example where you just have 2 edges, you will, for example, see this as a generator. And maybe I'll just write it on the board, just to have this as an example for those who have not seen this before. So for example, this C1, Y3, 2, C1, 2, this is mapped to X1, X3, X2 to the -1, X2, 3, and then it's X1, 2. And similar for the other one, I have C3, Y1, 2, C2, 3, which is mapped to X3. Then I have X1, X2 to the -1, X1, 2, X2, 3. And that's the same. So in particular, the difference lies in the kernel. Okay, and if you, and moreover, what you see is no matter which term order you choose and which is the leading term, none of these terms above will divide it. So there is more stuff inside. So then let's see what it is, and I won't give you the precise definition, I only want to give you the flavor, yeah.
Just to make sure I'm understanding, x2, 3, it's a separate variable than the x's, or is
it's a separate variable which corresponds to the edge 2, 3. So I have a variable for each vertex, and I have a variable for each edge. And that's the edge variable. So I only want to roughly describe how the Gröbner basis looks like. So what we show is there's a square-free Gröbner basis. So the leading terms are square-free, as we've also seen for like these binomials on the slide before. There I have, so which type of binomials do I have? I have the binomials which we've seen in the example before, which I'll have for every edge. And we call them fundamental binomials. So these have to appear. And then there are certain binomials which come from directed cycles in the graph. So there is a recipe to take a cycle and then somehow to direct edges in any way you want. And for each type of direction, you can cook up a binomial. And I won't tell you what. I will not tell you how because it's just complicated, but it depends on cycles. And similar, you can do the same game basically for, can do the same game for paths in your graph. Again, you start by directing edges, some in one way, some in the others, back and forth, and then again you cook up a binomial. And this can be done for every, what we call, every such zigzag pair, how we call them. What I want you to take away from the slide is that everything just depends on cycles and paths in your graph.
Would it help us to understand anything about the quotient ring for one edge? Like it's the same ring appearing multiple times. Like many of us studied Stanley Reisner rings, and Stanley had a generalization to glomming together toric rings along overlaps. And somehow you're glomming together rings on each edge, and I have no clue what that ring is.
It's, I don't think, okay, let's say it does not help us for if we want to understand these polytopes. That's what I can say, because
We're all in a good place.
okay, but maybe one thing I want to point out here also, if you're just interested in which of these binomials generate your toric ideal, you don't need the ones coming from paths in your graph. You only need cycles, and you only need the ones just from the edges. That's the other thing. Okay, so now I promise to speak about triangulations. And I have to give you a little bit of a black box, if you have never seen this. So there's a beautiful result by Bernd Stumpfeld, which basically shows if you have a Gröbner basis of the toric ideal, then this corresponds to, or if you have an initial ideal, more precisely maybe, this corresponds to a regular triangulation of the polytope. And moreover, if the Gröbner basis is square-free, then the triangulation is unimodular, which, coming back to Ben's talk yesterday, just means that the simplices appearing in the triangulation have normalized volume 1. So they are somehow the smallest lattice simplices you could think of. And so we now know by this result by Bernd Stumpfeld that these polytopes have a regular unimodular triangulation. And how does it work? So how do I go from my Gröbner basis to the triangulation? That's what I would like to tell you. Okay, so basically facets, the maximal faces of this triangulation, they correspond to monomials that are not divisible by any leading term. So let's go through this. So any monomial in Rg, here, so any monomial in Rg lives in these, is a monomial in these variables, basically. So I have the z variables, I have the y variables, I have the t variables. These correspond to lattice points, the way we just constructed everything. So every monomial in these variables corresponds to a set of lattice points, and in this way it corresponds to a simplex, by just taking the convex hull of these lattice points. That's the idea. And I've written this out here as well. So I have the ck variable, which corresponds to the unit vector corresponding to the vertex k. I have the cf variable corresponding to the unit vector to the edge f, and then I have like the ones which come from the vertices of the polytope. So now, if I want to describe some of these triangulation, it's rather tedious to write down all these sets of vectors, so I won't do this. However, what I want to do is I want to draw some pictures. And in order to be able to draw pictures, I want to represent, let's say, the first unit vector, the unit vector corresponding to this vertex k by a white dot. It's a white vertex. And don't ask me why we chose white, I don't know. Why we didn't choose black in this case, it's white. Anyhow, as similar, this unit vector corresponding to the edge f should just be represented by a usual edge. The vertex ei minus ej plus ef should be represented by an edge directed from I to j. And similar here, this should be an edge directed from j to I. And finally, this weird vector where we have a minus for the edge, we will draw such a wiggle edge. And I've also written this here so that it's hopefully easier to follow, but it's also in this picture over there. I've also put it to the vertices of the polytope and to the line points.
Martina?
Yeah.
So this wiggly edge, does it have a meaning?
No. You can, I mean, you could choose, I don't know, you can also just take a colored edge, whatever. I just need a symbol. I just need a symbol to distinguish it from the other type.
This is all motivated from physics still.
It's motivated from physics, but you can take any other type of edge, to be honest. Yeah. So for example, let's say, if I would like to represent this monomial here, what am I going to do is, so I have the variable C1, C3, so I take my vertices 1 and 3 as white vertices. That's the first thing. Then this y1, 2 tells me I have the directed edge from 1 to 2. This C1, 2 tells me I have the undirected edge from 1 to 2. And finally, this T2, 3 tells me I have this wiggle edge from 2 to 3. Yeah.
And the black dot is because
two
is not there.
You can also omit the dot.
Okay.
But it's nicer to draw if you draw a dot. The pictures look nicer.
Should we be thinking of the white dots as loops in the graph?
No.
Okay.
No. Please don't.
Let's try.
Okay, now let me give you the facet description for the case that we have a path of length 1, so just one edge or two edges. So this is the pictorial representation which we get, and we will go to this example in a moment. And that's a representation you would get for a path of length 2, so two edges. So let me maybe go to this example to make it a little bit clearer, again, how this works. So one way to triangulate would be this way. And then what I'm just saying is, okay, this triangle corresponds to, I have the vertex 1, I have the undirected edge from 1 to 2, and I have the directed edge. Same game here. I have the vertex 2. I have the undirected edge from 1 to 2. I have the directed edge from 2 to 1. In the middle, I have the unit vectors, all of them. So we just have both vertices, and I have the undirected edge. Here again, I have the unit vectors corresponding to the vertices, and then I have this wiggle edge. And that's what you see in this first row. And you can play the same game for paths of arbitrary length. So if you start counting, then what you see is we have 4 facets and then we have 16 facets. And Ben told us that if we want to compute the normalized volume, if we have a unimodular triangulation, we can just count how many facets it has. So the number of facets in this triangulation give us a normalized volume. So then you have 4, you have 16, then you will have 64. So it's not hard to guess that the normalized volume of a path with n edges is 4 to the n. And the same is true if you take any tree on n, actually n edges, not n vertices. Should be n edges, sorry. And for the n cycle, which is maybe the next case, again, you see a really nice normalized volume. It's 4 to the n minus 2 to the n. So you somehow lose something. And I should also say that these results above here, they were already known. So this was also shown by Lukas Hühne and Leonid Monin in their paper. So for trees, they had the normalized volume. They didn't know it for cycles, and they didn't have a triangulation.
Does the answer depend only on the chromatic polynomial?
know. It's more complicated. And we don't know. I mean, we don't have a complete answer. So the question now is, what else can we do with this triangulation? So now we have a triangulation. Yeah. We now have a triangulation, and we can describe the triangulation for trees and for cycles and for paths and very explicitly. And I recommend, if you ever want to read this paper, skip the part on trees, because it's somehow nice to describe, but it's very hard to prove. It's just a lot of combinatorial things, and I wouldn't read it anymore. So I don't want to discourage you, but still, yeah, sorry.
I was just curious if you can see from the graphs somehow which simplices are adjacent to one another. Like,
What simplices and faces?
Yeah, which simplices are adjacent by a maximal face? Like,
Yeah.
you can see that by looking
Yeah,
at
you can see basically you have to compare the symbols. And by symbol I mean types of edges and vertices. And if they intersect in a face of codimension 1, then there's just one symbol which differs. Because this just means there's one vertex which lies in one but not in the other. Okay, so we had this yesterday. However, I want to recall it because I don't think that everybody is really familiar with it. So let's go a little bit into Erhard theory. So what's the Erhard polynomial? So let's say we have a lattice polytope of dimension d in R to the n. Then we can dilate the polytope by a factor of t, and we can count lattice points inside this polytope. And this is what I call LPT, LP of t, which is also called discrete volumes. I count how many lattice points do I have in the t dilate. So for example, if you take this cube of dimension 2, you have 4 lattice points in the first dilation, then you have 9, then you have 16, and it's not hard to see that in the t dilation you have t plus 1 squared. So what you see in this example is a polynomial, and also, if you do it for higher dimensional cubes, you will have t plus 1 to the d, because on each coordinate axis you have t plus 1 points. And in general, the same happens, namely LP of t is always a polynomial in t, and the degree is the dimension of the polytope. And this was shown by Erhard, and that's why it's called Erhard polynomial. So now, if I have this polynomial, we can take the generating function. So we just sum up. So we start with 1, and then we have like sum t greater than or equal to 1, and then I take the number of lattice points in the t dilation times c to the t. It's just a generating function, and since I know that this is a polynomial, I know that I can write it as such a rational function. And in particular, in the denominator, we have 1 minus c to the d plus 1. And this polynomial up here, that's what's called the H star polynomial. And we heard yesterday from Ben, if you plug in c equals 1, then you get the normalized volume. Okay, so that's the H star polynomial. So what else do we know? So first of all, the coefficient H0 star, it's always 1. This coefficient H1, that's always the number of lattice points minus a dimension minus 1. This we also know. This we can just explicitly write down what it is. If you plug in 1, as I just said, it's a normalized volume. So it's the usual volume multiplied by d factorial. And in this sense, the H star polynomial refines the volume. And then there is this beautiful theorem by Stanley who showed that these numbers are not only integers, but they are also non-negative. Okay. And so what's the goal now? We would like to compute these H star polynomials at least for specific graph classes for these cosmological polytopes. So what the first thing we can do, the first thing is if you klug together two graphs by just identifying them along a vertex. So you have G1, you have G2, you take a vertex here, you take a vertex here, and then you take what is called the one sum. Then what's happening on the level of H star polynomial is that these polynomials just multiply. And I should say that the proof of this fact is purely algebraic. It's not a geometric proof, it's just uses the toric ideal and the generator, that we know a generating set. So in particular, if you take an edge or a path of length 1, you will just get 1 plus 3c. And this 3, as I said, it's a number of lattice points, which is 6 in this case, because it has 3 vertices and 3 unit vectors, minus a dimension, which is 2, because I have a triangle, minus 1, which is 3. So just as a check. Okay, so from this, we now directly get that the H-star polynomial for any tree is just 1 plus 3c to the n. Because you can build a tree by just adding edges and gluing them along a vertex. In particular, this directly recovers the normalized volume by just plugging in 1. And that's why I said you shouldn't read the other paper. Because it's easier here. It's like, or not all of the other paper, let's say, at least not the tree part.
Okay.
Yeah, sorry.
So you said is the one sum of the graphs, the cosmological polytopes are not joins or free sums or anything. It's not. You're saying it's not a geometric phenomenon.
It's kind of a generalized direct sum, let's say. So, but it's not a join. So, my first thought is that it's a join, because also the triangulations don't work at all. But then the easiest way is just to go through the toric idea. You had a question.
Oh, I was asking about the triangulations. I was asking if you can see this product structure in H vector.
Not at all. Unfortunately, no. That's what I hoped. I saw it, that's a join. And then I was, had to admit that it's not the case. Okay, so what else can you do with this result? So you can, as I said, you can also take graphs with multiple edges. So now let's say I take a tree with multiple edges. It's not really a tree, but I don't have a better name for it. So what I just mean is you take a tree and then you are allowed to have multiple edges between each. Between each pair of vertices. So, and the notation will be like, for example, here 1, 2, 3, 3, 3, 5 just means, okay, I have one edge with kind of multiplicity 1. I have 1 with multiplicity 2. Here's 1 with 3, 3, 3, and then 5. So, and we already know by this one sum result that we only need to compute the H-star polynomial of a multiple edge. And that's what we are doing. So we use what is called a half-open decomposition, and there we need the triangulation to compute this H-star polynomial of such a multiple edge. And again, it factors really nicely. So for example, now, let's say if A equals 1, then you will just recover the H-star polynomial of an edge, because then this is 1 plus c to the zeros, and this is 1 plus 3c. That's again what we had. And now putting everything together, you get this product formula for the H-star polynomial of trees with multiple edges. So now let's go to cycles. So for the n cycle, again, using half-open decompositions, what do we show? We basically show that the H-star polynomial is just the H-star polynomial of a tree, and then you subtract 2 to the n to the c to the n. So you've seen this 2 to the n before, because it also appeared for the normalized volume. But what was kind of strange and maybe unexpected, that this 2 to the n is really just in this highest degree occurring. And all other coefficients are the same. And then having this, you can go on and don't read this formula. And you can just take a cycle where you allow multiple edges. So it's the same game as before. And here, I think what I only want you to see in this formula is, again, if you compute the H-star polynomial, you will have the H-star polynomial of the corresponding tree with the same multiplicities. And then there's a correction factor. And again, in this correction terms, you have, again, this 2 to the n, c to the n. And then there's something else which comes from the multiplicities. In particular, if you plug in a equals 1, then you recover this above. And the method is, again, a mixture of half-open decompositions and one sums. Okay. Yeah. Now, okay, mathematically speaking, I would say this triangulation is nice. However, if we think back to our motivation, namely we want to compute these canonical forms, are they really nice? So, I mean, if I would ask a physicist, what would he say? So let's try to argue. So I guess a mathematician would say yes, because we have a nice combinatorial description. It's a unimodular triangulation. So it's like the nicest type of triangulation we can think of. We can compute normalized volumes. We can compute H star polynomials. So what do I want else? It's nice. Okay. However, if I were a physicist, I guess I would say no, because for several reasons. First of all, this triangulation does not really extend nicely from subgraphs. So it's not that I can somehow step-by-step build my graph, even for my triangulation. Even for trees, this doesn't really work. And second, it's just too big. If I want to compute like this canonical form, I would rather like to have a triangulation with as few simplices as possible, because then I have to sum up less stuff. And I mean, here I have 4 to the n many facets, even for trees. So like in this direction, yeah, okay. So the question is, can we find something which is more linear?
If you have bigger triangles, do you have to scale the size of the canonical forms you sum up? It's like a weird question. Okay, it's just ones always. Okay.
So for trees, we can do by far better. Let's say for trees, it's not hard to see that there is a canonical triangulation which does not use 4 to the n facets, but 2 to the n minus 1. And the basic idea is just if you add an edge to your graph and you just glue it along a vertex, what's happening geometrically is that you're taking a bipyramid and then you take a cone. And then you're just saying, okay, take the old triangulation at this point or this point to the facets, and then to each facet at this additional cone point. And in this way, you can really compute these canonical forms now. We did it for certain examples. We are far away from understanding them in general, but this is now doable. Yeah, so that's why I said it's easy to describe. It extends nicely just by the description I just gave you. And it has by far less cells. Okay, now I have about 10 minutes, I guess. So let me throw some more beautiful combinatorics about these polytopes at you, and also some mysteries which you just don't understand. So there are a lot of questions. So let me give you another nice triangulation. So let's again consider this case that we have a path with n edges. Then what one can show is that there exists a unique regular unimodular triangulation with the following properties. So first of all, this triangulation respects the graph symmetry. So I mean, I have like this obvious symmetry of my graph if I have a path. And it would be nice if I can somehow see this on my triangulation. So that's the first property. But maybe more striking, if I look at the dual graph of the triangulation, it's the 4 by 4 by 4 by 4 grid. So the dual graph is just saying, take a vertex for each facet of your triangulation and connect them by an edge whenever the intersection of these two facets has codimension 1. And I can show you 2 examples, I guess. Yeah, okay. And moreover, this triangulation is a cone over unit vector. So we can say more. There is a triangulation for each of the unit vectors such that it's a cone and that we have this dual graph. But there's just one which is symmetric, where it takes a unit vector which corresponds somehow to the midpoint of the graph in a certain sense. So how does it look like? So in this case, for the one edge case, it's not this triangulation, it's this one. So here you have, I mean, that's also one way to triangulate. And in blue, I've drawn the dual graph. And you see that if I apply the graph symmetry, I get this one. From here, I get to this one. So this is exactly what I want. And in one dimension higher, it's this triangulation, and don't look at it too deeply. I just put it in the way that this already gives you the 4 by 4 grid. So like that's also, I mean, I put him in the order how the dual graph would look like, that you can see the grid. Okay, and yeah, I mean, I just found it nice that this is happening. So more. Okay, so what about secondary polytopes? I won't tell you what a secondary polytope is, but that's just maybe it's now for expert. So, but roughly, vertices of the secondary polytope, they correspond to regular triangulations using only the vertices of the polytope. So you can run some computations, and then that's what you see for the path. So for the path, let's say here, let's go through it. That's a path where I have two edges. So the polytope has dimension 4. I have 6 vertices. The dimension of the secondary polytope is then 1 because it's 6 minus 4 minus 1. And I have 2 vertices, so that's just an edge. Now here, if I have 3 edges, the polytope already has dimension 6. I have 9 vertices, so 3 times the number of edges. The dimension of the secondary polytope is already 2. So it's 2-dimensional, I have 5 vertices. Next case, if I have 4 edges, I'm in dimension 8, I have 12 vertices, the dimension is 12 minus 8 minus 1, so 3. I have 14 vertices. And you might recognize the numbers, yeah. And indeed, we see a tetrahedra here. And somehow, these also appear in physics, and that's why I show you this picture. So like cosmologists, they also care for these polytopes, and I will tell you a little bit more in some minutes, they try to compute like the differential equation satisfied by these cosmological wave function, and also there's a tetrahedra pop up. However, there is a shift, so I think the right picture in their case is already for the case where you just have one edge, and so there is somehow a shift, but again, we don't really understand what's going on, why we see these coincidences. So let's say I have 2 mysteries now. First one, so as I just said, so there's like what is called this cosmological wave function, and what cosmologists want to do is they want to try to compute differential equations that are satisfied by this wave function. And so usually what they do is they try to model these differential equations using what they call marked graph tubings. I will show you a picture in a minute, so you will see what it is. And if you do this for the path on n vertices, they have 4 to the n graph tubings. And remember, 4 to the n was a normalized volume. So if you try to go from graph tubings, these are graph tubings now, to facets of our triangulations, you can come up with kind of a natural bijection. However, I have no idea why. I mean, there is a bijection just on the combinatoric side, but I have no idea what it means for the physicists. Similar, for some reason, they take these graph tubings and they refine them. So somehow they come in different layers and different levels. And in the case for the path with 2 edges, the way they define them, they have 1, 5, 7, and 3 tubings in certain groups. Yeah, if you take the alternating sum, you get 0. So this looks like an Euler characteristic, and it is. It's the F vector of, if you take just an edge and then a threefold cone. So just take 3 triangles which you glue together along an edge. If you go to a path of 1 length more, same game. So they refine the refinement, which somehow makes sense for them, is like this 1, 8, 22, 24, 9. Again, alternating sum equals 0. Again, it's an Euler characteristic, and it's the F vector if you take a threefold cone over the complex before. And this goes on. So you can explain why this is happening, but I don't know what, in a sense, why. Like what's behind? And next thing, which for me is even a bigger mystery, so I should say that they are extremely good in coming up with combinatorial models. So whenever you talk to them, they tell you, there's another model. You could do it this way. And like several weeks ago, they told me, yeah, we have a new model for our differential equation. And this time, what they were doing is they were taking cubes, and they were labeling faces of the cube by their graph tubings. And they had a collection of disjoint cubes. So that's like this new model which they came up with. And if you start some counting there, the following happens. So if you do it for the path of length 2, what they have is they have one two-dimensional cube, they have two edges, so two one-dimensional cubes, and they have one vertex. So actually, let's draw this, because then it's easier to count, because I need some counting now. Let's actually put it here. No, I think this you can't see. Okay. So that's a model. And now if you start counting, let's say you count how many two-dimensional cubes do you have? So you have 1. How many edges do you have? 4, 5, 6. How many vertices do you have? 4, 6, 8, 9. If you plug this into a polynomial, you have the H star polynomial. And similar, I mean, on the other hand, you could also play another game. Count some total number of faces here of this cube, so except the empty one. Except the empty one. So this has 9 faces. This, if you take the two edges together, you have 6 faces. If you take the vertex, you have 1. That's another way to get the same number, same polynomial. And it's kind of striking. And it also happens, in bigger cases. And okay, what you can do is, you have like these graph tubings, which somehow correspond to the faces, and to the faces of this complex, and then you can cook up a triangulation here. And such that, we also have this bijection from tubings to faces of the triangulation. You take a Schelling of this triangulation, and there seems to be a Schelling such that the corresponding faces here contribute to HI when they should. But that's just the geometric and combinatorial side. I don't know why. There should be more. And with this, let me come to my last slide. So what can we do, or what is open, what are we trying to do? So we are now trying to compute these canonical forms finally explicitly with Dan Bass and Claudia Febola. Then at some point I got the question from Bernd Sturmfels, so can we somehow read off the canonical form from the Gröbner basis? And it should be expected because some of the Gröbner basis knows everything about this polytope. So it's not, but we don't know how. And the other thing is, can we somehow understand what's going on there really? And this is, we are talking to physicists, so Daniel Baumann and Harry Goodhue, they are cosmologists who are based in Taiwan and Amsterdam. But so far it's hard, let's say. It's nice to talk to them, but it also takes a lot of effort. Then there is a particular facet which is called the scattering amplitude facet, which is, so the projection of this facet gives you actually the symmetric edge polytope, Ben was talking about yesterday. And so what's the role of these facets for physicists? We don't know. The other thing is, so we could, and I didn't show this to you, we could find lower bounds for the coefficients of the H star polynomial. So what about upper bounds? We have a conjecture, but we were not able to show it. Similar, can you compute these H star polynomial for other classes of graphs? Again, there are some conjectures, but yeah, let's keep it for the future. And then currently, I have a PhD student, so Tom Donzelmann, who is joined with Christoph Thiele in Bochum. And Benedikt Rednos is a postdoc of Christos, and we are trying to look at these polytopes for random graphs. Yeah, and I think that's everything.